Thank you again for taking the time to watch this video. I know it's a little time consuming to get on the internet at home and watch these videos, but I'm thinking that if we work problems in class, it's going to be more beneficial to you if I cover the basic information, plus you have the benefits of being able to pause this video anytime you like, so that if you don't get all the notes done, I'm not flipping screens on you and not having to waste class time when we go back. So today's lesson, 2.5, and we're going to talk about complex zeros and the fundamental theorem of algebra. As the name implies, this is going to get to a very important theorem, and we're going to be kind of finishing off what we've been talking about with the whole idea of polynomials and how many solutions that they have. Today's lesson, we're going to talk about two major theorems. Actually, one's major, one's kind of minor. And we probably won't get to the complex conjugate of zeros and factoring with real number coefficients, but I'll at least introduce it to you so that when we come into class tomorrow, we'll hit the ground running. We'll be able to move forward faster. These topics really round out the chapter for us, and you'll see why as we get through it, but it does kind of complete the story of zeros and the factors of polynomials. I've got a lame joke. Maybe. Oh, too far. Great, there we go. And the wife's going, what was that noise outside, Marvin? Because it was nothing. And of course, there's a zero tapping at the window. Because we are talking about zeros, which are the same thing as solutions. It's probably good for me to write this down. We've been talking about a lot of words that mean the same thing. We've talked about zeros. We've talked about solutions. We've talked about crossing the x-axis. These are all sort of referring to the same thing. Zero means when does your function equal zero? And use the quadratic formula if it's quadratic, or if it's a linear equation to solve for y, or when x is zero and figure out what the y solution is. And we sometimes talk about those as solutions, and of course crossing the x-axis. And that's kind of where we're going again today. As you know, if I give you a polynomial function, let's call this one f of x equals, looks like x squared minus 4, and you graph it, you get the graph that I've shown there. You can observe the graph and notice, hey, it crosses the x-axis at -2, and then again at +2. And we would say the solutions for this are x equals -2 and x equals +2. As a matter of fact, x squared minus 4 is the difference between two squares, and it's easy enough to factor and solve. It factors into x minus 2 and x plus 2. And setting those equal to 0, giving us the zeros, gives us the same solutions, 2 and -2. The other thing you know about this from looking at the graph, hopefully, is because it crosses the x-axis twice, you know that the leading coefficient, or the leading term's exponent, has to be an even number. Both limits are going up in the same direction, and it's got to at least be 2 because it crosses the x-axis twice. But it doesn't have to cross the x-axis twice. I can give you another quadratic polynomial that looks a little different. This one is f of x equals x squared plus 4. This one does not cross the x-axis at all. It's up too far. But if I take you back to what we talked about at the beginning of the year, we talked about something called complex and imaginary numbers. It's true that this polynomial does not have any real solutions because it does not cross the x-axis, but it does have two solutions. And we can find those zeros or solutions by simply setting x squared plus 4 equal to 0 and solve it. Subtract 4 from both sides. We end up with x squared equals -4. Take the square root of both sides. And we end up with x equals, now remember when we take the square root of x squared, we've got to consider both the positive and the negative solutions, so it's x equals plus or minus the square root of -4. If you recall, when we were dealing with imaginary numbers, we can take out the square root of 4, that's 2. That leaves us with the square root of -1, which we defined as I. So this has two solutions. X equals 2i, and x equals negative 2i. Those are imaginary solutions, but they are solutions nonetheless. And this takes us to what is the fundamental theorem of algebra. And that theorem states that if you have a polynomial function of degree n, like x squared, degree 2, and then it has n complex zeros. They could be real, they could be imaginary, or they could be a combination of real and imaginary and complex numbers. And they may be repeated. They may have a multiplicity of 2. But there will be n solutions to a degree n polynomial. So if I give you a polynomial that is f of x equals x to the 4th power plus, and I don't even care what the remaining terms are, there will be 4 solutions. Maybe all 4 are real numbers and cross the x-axis 4 times. Maybe 2 are, maybe 0. Maybe just 1 is repeated 4 times. But you will have some combinations. It may be, some may be real, some may be repeated, and some may be complex. But it will add up to 4. Let's do an example so you can see what I'm talking about. If I give you the function f of x equals x cubed minus x squared plus 9x minus 9, I'm claiming that this has 3 solutions. I just don't know how many of them are real and how many of them are complex. We can go through the same steps we went through in our problem today. I can use the rational roots theorem. The rational roots theorem says, take the constant term, 9, and find all the factors of 9. 1, 3, 9. Find the leading term's coefficient, which is 1, and find all the factors of 1. 1, that's easy enough. The possible rational roots are x equals plus or minus 1, 1 over 1, plus or minus 3, 3 over 1, or plus or minus 9, 9 over 1. We can even graph to see if we can figure out what those, which ones of those we want to test. And hopefully I've still got it up on the graphing calculator. Yeah, it's not very exciting. I'll add that drawing. Go back. And I'll put the graph over here. And we can see, looking at the graph, that it does look like it crosses at 1. Let's see. And here's the graph. I don't think I need to make it bigger. And now to figure out what the other solutions are, I may want to try to simplify this. Let's take 1 out of it. In other words, divide this by x minus 1, because we think that's one of the solutions, and see what's left. So I'll use synthetic division. 1, and then my coefficients are 1, negative 1, 9, minus 9. I'm going to just divide by x minus 1 to sort of simplify the equation. 1 comes down. Minus 1, 0. Just work through this quickly. And I am left with no remainder, which does indicate that 1 is a solution. So x equals 1 is one of my 3 solutions. There's 1 down, 2 to go. And I'm left with the polynomial x squared plus 0x plus 9. I now set that equal to 0 to find my 2 remaining solutions. X squared equals negative 9, and I'm left with x equals plus or minus the square root of 9, which is 3, because it's negative 9i. So it looks like I have 2 imaginary solutions, 3i and negative 3i, and I have 1 real solution, 1, but there are, again, 3 solutions. Now, one of the theorems that goes with it, I don't consider it a major one, but it's a minor one, is this fact that if I've got this polynomial, x cubed, well, let's just go to the next screen, and I'll rewrite it for you. If I've got a polynomial like f of x equals x cubed minus x squared plus 9x minus 9. This theorem says I can write it as the product of all of my factors. So I factor this, and I find that my solutions are x equals 1, x equals 3i, and x equals negative 3i. The linear factorization theorem says I can write this as a function of those three solutions by simply putting each solution as the minus term. So x minus 1, x minus 3i, x minus a minus 3i becomes plus 3i. This is saying that I can write my polynomial either as a cubic equation or as the product of three linear equations, x minus 1, x minus 3i, x plus 3i. And if I FOILed and multiplied those three terms together, I would come back to the same equation. So let me read the theorem to you and go through it again. If f of x is a polynomial function of degree n greater than 0, in other words, you've got something other than x or higher. F of x has precisely n linear factors, three linear factors because I was dealing with the cubic. There's 1, 2, 3. I forgot you can't see my finger pointing at these. And that you can write those as x minus each one of the solutions. X minus 1, x minus 3i, x plus 3i. And that's useful for identifying the zeros and being able to understand how the function behaves. Once again, here's to recap. Here's the following statements about a polynomial function and their equivalent. X equals k as a solution if f of whatever that number is equals 0. That's the remainder theorem or the factor theorem. K is a 0 of the function f. That's just saying the same thing. If x equals k is a solution, then you could say k is a 0, and that's where it crosses the x-axis if it is real. If it is imaginary, it does not cross. And you can write x minus k as a factor of x. So here's what we're saying. If you've got the polynomial function f of x equals x squared plus 5x plus 6, you plug it in, use the quadratic formula, and you find that the solutions are x equals 2 and x equals 3. We would say x equals 2 is a solution, x equals 3 is a solution. We would say that 2 and 3 are zeros, meaning it's going to cross the x-axis, because these are both real numbers, at 2 and also again at 3. And then finally, we can write these as factors, x minus 2, x plus 2, x plus 3. Jeez, I just messed the whole thing up. X minus 2 is a solution, x equals minus 3 is a solution. My apologies. Did this too fast. But anyway, it factors into x plus 2, x plus 3, x equals negative 2, and x equals negative 3 is a solution. I made a mistake, and I'm sure you were sitting there catching me and so forth. You tell me about this tomorrow when you come into class. I will give you a piece of candy. So, but you got to tell me and don't tell anyone else that. Okay, so let's try one more, and then we'll call it a day, since I'm obviously getting tired too. Write the polynomial function in standard form, identify the zeros of the function, and the x-intercepts of the graph. Here we have an equation that's given to you as in linear factorization form. They've given us both the factors. I don't know if you can see this very well on your computer screen, but since x minus 3i is one of the terms and x plus 3i is the other term, that implies that the two zeros are x equals 3i from the first linear factor and x equals negative 3i from the second linear factor. Those are my two zeros or solutions. However, since they are both imaginary, it does not cross the x-axis because they are imaginary solutions. I hope that reappears in a second. And the other thing we can deduce is that it's going to be, it's obviously a parabola, x squared, but it's going to be either all above or all below the x-axis. We can FOIL this to get the solutions. When we multiply it out, we'll end up with x squared, the middle terms will cancel out, minus 9i squared, If you recall, I squared equals minus 1, square root, you get minus 1. So this turns into x squared plus 9, and that is our function. F of x equals x squared plus 9. If I didn't make sense what I just did, if I did that too quickly, please ask me tomorrow in class. I'll cover one or two more slides, and then that will be it for the lecture, because there's the solution again. Because the zeros are not real, the graph has no x-intercepts. This will be a good place to stop. I will explain the complex conjugate zeros tomorrow in class, how when we do have imaginary or complex solutions, they do come in pairs, and that makes it a little easier to deal with. So thank you again for your patience in listening, and make sure to point out my mistake to me when you come into class tomorrow.